Hi students, okay, this is our last part 3 of chapter 1, Introduction to Statistics in Psych 218 or 218, Analysis of Behavioral Data. So if you're following along in your textbook, if you watched part 2, you can get the kind of inside joke there. Anyway, if you have a textbook and you're following along in the ninth edition, this would be 1.4 and we'll cover 1.4, 1.5 and so on. Anyway, whether you have a textbook or not, if you're watching these videos, you can still follow along, and this is part 3. And we finish off the introduction to statistics with variables and measurement and how we can measure these variables and data that we would use for statistical procedures. So let's get right into it. So you remember we have defined the term variable as characteristics that change across individuals in a study group or experiment, I should say, or study a group or an experiment. And so because we are asking questions about people, again, this could be anything, shoe size, temperature, whatever. And so for each person that we ask, there is going to be a score for each person for that variable. So when we obtain these scores, then we can use these scores to answer questions about the variable that can help us explain about behaviors that we can observe. Again, it could be how much you sleep, how much you study, could be how much water you drink, anything. Any observable behavior that can be observed and measured, we can measure those as variables using data. And so the next part is, well, how do we measure that? And what kind of data are we measuring? So for example, would we measure temperature in the same way we measure, I don't know, your IELTS score or a test in this class or the number of hours you're awake? Or even the letter grade that you get from this class or in your other classes? Again, each of these would have a different measurement, right? And you can think, oh, well, just like there's a different ruler for feet as there is a different ruler for centimeters, metric or imperial, or like centigrade or Celsius and Fahrenheit, there are different tools of measurement, and we're going to explore that. So, a couple things in terms of variable that we want to define here to help us understand this and take this for the rest of our class. We want to make sure we understand two things. One, a construct, and two, an operational definition. So the construct itself is some kind of attribute that people have that cannot be directly observed. So I'll give you an example here. Remember the one that we had for aggression? We can be a positive here and think about, I was going to write something else. Happiness. Again, we can see somebody smile or we can see somebody angry, but these are constructs, abstract things, because, well, it is not directly observable. We can observe behavior that shows aggression or behavior that shows happiness, be it a smile or an angry face or other things. So that's a construct. Internal attributes or characteristics that cannot be directly observed. So that's what that means. And we use abstract terms like that to explain and describe behavior. However, because constructs are not directly observable, we have to bridge the gap. As in, we have to bridge the gap between a construct and an actual variable that we can observe and measure. So this is what we have the process of operational definition, which means we want to find a behavior that we can observe and measure that is linked to the construct. So for example, can you think of an operational definition for aggression? It could be a scale, or it could be the number of times somebody yelled at somebody else, or it could be number of times, somebody tried to hit somebody else. But happiness might be a little easier. You may count the number of times somebody smiled, or a survey that might measure that in a scale of 1 to 5, 1 being not happy, 5 being happy. So whatever way we make an operational definition to link a behavior with a construct, that's the process, that we want to link a variable with some type of characteristic about a person that we can't directly observe, but we can observe through some behavior that changes. And that's operational definition. Again, these terms would show up in your Psych 217 class. Now that we have operationally defined a variable, well, different types of behavior, different types of variables would have different characteristics. So, for example, we have two very distinct types here. One is discrete, and the other is continuous. I'll give you an example here if you're stuck. Think for discrete like integer, like 1, 2, 3, 4. And I'll make this even easier. Think persons or people. You can't cut a person in half and that person will still be alive, and you don't have 1.5 people. So they're whole numbers. You can't have anything in between. There are no values between the two numbers or categories. It could be blue, red, yellow, and so on if you just want the colors. You can think of, oh, well, technically there could be like different shades of red or blue. Well, if you're thinking that, you're thinking in the continuous variable type here, that we can have numbers and values in between. So that would mean, for example, 1, 1.1, 1.2. I'm just using one decimal point here, and so on all the way up to 2. If you can think of your percentages, yeah, that would be a continuous variable. It could have a potentially infinite number of parts in between. You can have 1, 1.01, or 1, 1.001, and so on. That would be a continuous scale, a continuous variable. And so there are two types of variable: discrete, you can think of whole numbers with no values in between them and the categories, or continuous variables where there could be equal parts that is potentially infinite between the categories. So that's our first distinction with the types of variables. And here is an example of a continuous variable. Here you can see you can have decimal points in these numbers. And this also shows the next point about real limits too. So here you see between the category of 149 and 150, you can have anything in between. 149.6, 149.5, it could be 149.4, etc. And these points exist. These decimal points can exist between these integers. And this would make the variable continuous. And we would measure it as a continuous variable. One concept here that we're going to talk about using this picture is this idea of real limits. So here's an example of what we're going to talk about. When we measure something, and imagine for a moment that you have a ruler. And so let's say if there's a person who is, and we'll use centimeters here. Let's pretend these are centimeters. This is realistic enough. Somebody could be 150 centimeters or 149.5 centimeters. But when we measure with a ruler, for example, if we say that person is 150 centimeters and we test and we measure this person, more than once. Often we just measure the person once and say, oh, well, this person's like 150 or 151 or 150 and a half. But if we do this enough times, sometimes you might go, oh, wait a minute. The person's standing the same way, but I'm getting somewhere between, 149.9. Okay. And another time, oh, I measure again, that person is 151.1. So then what do we say? Do we say that person is still 150, or do we go back to 149? And if you're thinking, oh, I can round up or down. Well, that's the thing about real limits. And we're going to show you this. So in short, before I go to the next slide, we would consider in a continuous variable that if you measure something in these categories of 149 or 150, 151, and 152, if you got a score of that is between 1/2, this is the lower limit for 150. So for 150, the lower limit here would be 1/2 down between one category and the next. So you can have between 150 and 149 going down, 1/2 from that. So because 150 is 1 away from 149, 1/2 that would be 0.5 lower than 150, 149.5. And then the upper limit for your 150 would be 1/2 of the distance between 150 and 151, going from your point to the next one up. So that's your upper limit. Okay, here LL stands for lower limit. UL stands for upper limit. Excuse my writing. And so when we take a score, it happens to be within, let's say, the upper or lower limit of 150. It could be a 149.6. And the idea of 150, I'll change this one, it's 150.1, 150.2. Well, we would still consider that quote-unquote 150. Now, one way to help you remember these upper and lower real limits is the idea of rounding up and down. So, just like when we round up anything that is 0.5 or higher to the next integer, and we round down anything that is 0.49, let's say anything lower than 0.5 to 0.0, and we still call that number 150, for example, we're working with upper and lower limits. So this rounding up and rounding down, in statistics, we call that upper and lower limit. So real limits are important because we very, 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 very rarely actually hit that exact point. So like somebody is not, like if you try and measure somebody, would that person be exactly 150 centimeters? That person might be a little more or less than that. Another point here to show you how precise things can be and why we need real limits is the idea of time. So for example, if this class starts at 5 p.m. sharp and we want to be really precise about this, it would be 0 minutes, 0 seconds, and 0.000 milliseconds. But that's only one brief, very, very brief moment in time. And so as soon as you hit the next second or the next millisecond, even something like this, 1 millisecond, that's not 5 anymore. Just like before, you could have 4, 59, 59, 999. That's not 5. That's 1 millisecond before 5. Just like this here is 1 millisecond after 5. So there's only one brief moment in time, depending on how precise you are with this, to say, that's exactly 5 o'clock. So because we can't always or very rarely actually hit the exact point in a continuous scale, we have upper and lower limits. So these limits exist in pairs, and we have the upper and lower real limits. So the top of the interval, that is 1/2 of the distance between the scores. So I'll use the easier one here. So let's say instead of 99, and actually, you know what? I'll make this a minute so it's even easier. So 5, 5. Okay. And so 1, and this is 59, like that. So we have 1 minute but for each category. So we have 4:59, that's 1 minute before 5. And the next minute would be 5:01. So in terms of limit, following this rule here, you would have, okay, the upper limit for 5 p.m. if the continuous variable has intervals of 1 minute each, then the upper limit for 5 would be 5. Well, what do you think? What's half of 1 minute? So then it would be 5:00:30. That's the real upper limit. And the upper real limit. Okay? And the real lower limit, or lower real limit, would be 4 minutes, 59 and 30 seconds. So there is still a minute gap for the real limit of 5 o'clock. Now, mind you, when I do actual time, I just go right by 5, and if you're 1 second after 5, or if I can count milliseconds and you're after that, that is still after 5. For a statistics class, I am that strict, just to show the class how statistics can be really precise. But again, when we work with low real limits, we do count the half the distance between the intervals. Again, 1/2 interval down would be the lower real limit, and the 1/2 interval up would be the upper real limit. So there you go. So when you get practice questions on this, make sure you know several things when it comes to continuous variables. One, you need to know what the categories are. Usually they're numbers, and how far each category is, or each number is between them, and then you need to find half of that distance up or down the number you're looking for. For example, it could be 5 o'clock, it could be 150 centimeters, it could be 50%. Anything that is on a continuous scale, and figure out what the real or upper real limit and the lower real limit is. So make sure you find the practice questions in your textbook and other sources to practice this. This is an important one. Next, we move on to scales of measurement. So once we figured out, okay, for continuous scale variables, we would have upper and lower real limits. Then the measurement itself has different scales and different categories of measurement. So for example, you can have categories where it's just names. For now, we'll use gender as male, female, or non-disclosed or non-binary or other things. But yeah, they're not numbers, they're names. Single, married, common law, separated, divorce, things like that. Again, they're not numbers. They're names, which is why it's nominal. And you're not supposed to rank these either. So again, it's no particular order. They happen to be names. So that's a nominal category. Notice these categories could also still be, numerical as well. And numerical categories could be continuous or discrete depending on what you're asking. So some examples of numerical categories could be inches, pounds, seconds, minutes, and so on. Once you figure out the category of the measurement, you would also want to figure out the scale as well. For example, you can have a nominal scale. That is, for example, elementary school, secondary school, or post-secondary school, or numerical scale, 3 feet, 4 feet, 6 feet, 7 feet, and so on. And depending on the scale we use, we can also figure out the relationship between these categories. So here is a table showing the different scales of measurement and the characteristics and examples that follow. First, we have the nominal scale, where these categories are just names. They have no particular order, and so the slide says here they have no quantitative distinction. So gender is an example. It's nominal, just names. And another example is diagnosis, positive or negative, whether you have something or not, or the condition itself, whether it's experimental condition or control condition, just names. Okay, the next one is ordinal. They're still names, but there is some order to them, usually by size or magnitude. So for example, your rank in class or your letter grade, D, C, B, A, those would be ordinal categories. They're not numbers, but they have some order to it. Clothing sizes is another one, small, medium, large, extra large. Or like Olympic medals, first, second, third. Here in this case would be bronze, silver, and gold. We can also have two other scales that's going to be more continuous. We have the interval scale. Those are categorized ordered observations, and the intervals are equal in size. And they have some arbitrary 0 point. And what we mean here, there is a 0, but it's arbitrary. So it's not actually absolute 0. And we'll talk about this. So the first one here is temperature. We're not talking about Kelvin, where the absolute 0 is like no heat. But 0 centigrade and 0 Fahrenheit is just some point that is technically arbitrary, that is not 0 heat, but it's just 0 degrees centigrade or Fahrenheit. IQ, a 0 IQ does not necessarily mean that the person has 0 intelligence. It's just actually that it would not be possible because it's a ratio between a person's mental age, which is measured, and the person's chronological age. The average here is actually 100 because it's 1/1. IQ score is the ratio between your mental age and your chronological age times 100. And it's a standardized score. We'll talk about that. A golf score, the 0 is still technically arbitrary. It's for each hole. If you hit par, the number of shots you're supposed to hit, then you're not going over, well, that's 0 because you haven't gone over or under. If you hit fewer shots, and then they call that, oh, you're better at golf, then you score less. And if you take more shots, oh, you're a quote unquote worse player, you would need more shots, so you're over 0. Finally, the last one is a ratio scale, and that does have an absolute 0 point. We'll use some simpler examples here for this. Again, for the ratio scale. Again, for both interval and ratio, they are both categorized ordered observations, and they both have intervals of equal size. Again, to remind you here, the difference between interval and ratio is the ratio has an absolute 0 point. So here, the number of correct answers, you can get 0 correct, which is sad if you're a student and you want correct answers, but yes, it is possible. You could say, oh, 0 incorrect answers, that would be a lot happier. Again, you can get 0, and it does mean 0, like nothing. Again, the time to complete the task, you can technically complete the task in no time, or you haven't started, but the time itself is like 0. You haven't started or done it, or it takes no time at all. Yeah, or it's already done. Great, that's 0. A gain in height since last year, if you've already fully grown and you haven't gained any extra height, then it would be 0. So there you go. 4 scales of measurement. Nominal, just name only with no particular order. They're just categorized labels. Ordinal, they are categorized observations, but there is some order to it by size or magnitude. But the intervals are not equal. For example, a size small person does not have, let's say, a 5-inch difference between a size small and a size medium, I don't know, in terms of waist size or something. Again, I'm kind of making it up. Just like a better example would be for Olympic gold, silver, and bronze. The distance, the gap between a race, let's call it a 100-meter race, yeah, a person that scored gold may have a distance gap between gold and silver that is not the same gap as silver and bronze. It's not the same gap. Interval is a categorized order observation that has equal interval gaps and has some arbitrary 0 point or no 0 point at all. IQ has no 0 points, and golf has an arbitrary one, just like temperature. And the ratio scale is like the interval scale, except it has an absolute 0 point. You could get 0 correct answers or gain no height this year or last year. So those are the 4 scales. You definitely want to remember these. And again, depending on the variable you measure, you would use a different measurement scale. So here's our learning check for 1.4. Okay, so when a study assesses the optimal size, the number of members for a study group, the size of group in the variable here is what? Discrete and interval, or B, continuous and ordinal, C, discrete and ratio, or D, continuous and interval. Again, think about who you're measuring and what you are measuring for the group. Remember, we're measuring people, the number of people in the group. So the correct answer here is discrete and ratio. Remember, you can have 0 group members, like there's no group. You can't have minus groups. That's not possible. And you can't have half a person. So it is not continuous. It is discrete because you're measuring people one at a time. And you can have no group members, so it has an absolute 0. So it is a ratio scale. Discrete variable, ratio scale. Here's another learning check. So 2 true-false questions. A, variables that cannot be measured directly cannot be studied scientifically. True-false. B, research measurements are made using specific procedures that define constructs. Can remember here what words we use, what are the terms we used. Construct showed up already. That might be one term you want to think about. Operational definitions, another term you want to think about. So if you answered false for A, you're right, because we can still measure variables once we have operationally defined them. So operationally defining a variable links a variable, an external behavior, with a construct that is an internal state. You can measure the number of smiles for happiness, for example. For B, if you answered true, that is correct. Well, here we are using operational definitions to make sure that we're measuring the variable consistently and we're linking that variable to a construct. Last bit here before we're done for chapter 1 is the idea of statistical notation. And we're really close to finish here. So let's finish strong. Here in statistical notation, we're going to use several key mathematical symbols to make sure that each of us is using the same symbols to measure the same things and do the same procedures. So here are some symbols that we use. First, we refer to scores as X. And if we do correlation, we use Y also. These are scores to measure variables. Big N is the letter we use for population for the number of scores. This would be population size. And little n, small n, would be the number of scores for a sample. Again, population data, including the number of scores in the population, would be a parameter. And the little letter n here, the number of scores in the sample, being sample size, would be a statistic. So those are some terms we gotta know. X, big N, and little n. And because we are measuring different people and we want to include all the scores, we would definitely want to add them up. So one of the basic things we need is going to be something to show that we're adding up all the scores. And we use sigma notation to show this. That means we want to add up every single score that we're asking about, whether it's in a sample group, one group at a time, both groups, or something else. But sigma, the Greek letter sigma here, is going to be used for adding up all the scores. So when we have sigma notation, we say, hey, add them up, and then we want to add up something. So for example, we just want to add up all the x's. This would be x1 plus x2 plus x3 and so on until we're done. Okay, this will be xn here. If we want to do a bit more, x plus 1, this would be x1 plus 1 plus x2 plus 1. Oops, let me write that properly. x2 plus 1 and so on. Okay, so again, we want to make sure we add up the variables that's inside the bracket, including any operation that is included in the bracket. Bracket here is parentheses. That's the math term for brackets, the round brackets, that is. Okay. And this summation is done before addition and subtraction, other addition and subtraction. So again, using BEDMAS or PEDMAS, sigma notation is first. Okay. Parentheses. Here the B stands for brackets, P stands for parentheses. So now you know. So learning check. This is the last one before we're done. Take a look at this question. Question 7. What do we do for sigma x squared plus 47? Okay, take a moment. There's no parentheses here, so whatever comes after the sigma before any other operation sign, that's what you gotta do. So take a moment and think about this. So I'm just gonna write as a hint here. There you go. If you were to place a parentheses, that's what it would look like. And then you add 47. So remember, this is not the same as something like this. They're not the same. Okay? So what did you get? So if you answered B in here, square each score, add up the rooted score, squared score, sorry, and then add 47 to that sum, that's correct. What does that mean? Well, it means this. So again, remember we wrote this down. If we added parentheses, the x squared would be in those brackets, and then 47 sort of by itself. Once we're done the sigma notation, then we add the 47. Remember, we do the summation first. We do the sigma first before any other adding or subtracting. Okay, so it might look something like this. x1 squared plus x2 squared plus x3 squared plus whatever x squared, and those are in brackets, plus 47. Okay, so that's not the same, not this. It's not, this is not it. So it is not x squared, x1 squared plus 47 plus x2 squared plus 47 plus x3 squared plus 47. No, that's not it. Because the 47 is outside of the sigma notation. Okay, make sure you review this, because this is key for all the other chapters, including averages or means, including sum of squares, including variance, including standard deviation, including your descriptive statistics and your inferential statistics. So sigma notation is key. You got to get this. Make sure you practice. Let's try 2 more and then we're done. Sigma squared is equal to, in brackets, sigma x all squared. True or false? And B, sigma x in brackets times sigma x in brackets equals to sigma x in brackets all squared. Take a moment and think about your mathematical operations and see whether A is true or false and whether B is true or false. Okay, we're going to finish here. So for A, that's sigma x squared is not the same as sigma x in brackets all squared. Remember, for sigma x squared, you are squaring the scores first and then adding those squared scores. Whereas in sigma x in brackets all squared, you are adding all the scores first and then squaring the sum. So try it out. For example, in sigma x squared, it would be like, I don't know, 1 squared plus 2 squared plus 3 squared. Okay, I'm just going to stop right there. Okay, this would be 1 plus 4 plus 9, right? And this would be 14. Okay, if this was sigma x in brackets all squared, this would be 1 plus 2 plus 3 dot 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 all squared. Okay, so this would be 6 dot 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 squared. And even with just the 3 numbers, 6 times 6 is 36. Notice then, these are not the same. Okay, now for B, sigma x times sigma x is the same as sigma x all squared. Again, we can try this. 1 plus 2, so here's sigma x, plus 3. Okay, so we'll just stop right there. That is 6. Okay, and then we multiply this sigma x again, 1 Feels redundant? Yeah, that's right, because we're working with the same thing. And here's another 6. 6 times 6 is 36. Right? So here, my pen is not working on me. So that, with math, this would be the same as, oh, wait a minute. If I just do this once, it's 2 plus 3, dot, dot, dot. Oh, okay, if I do that, and I just square that number. Well, 6 squared is 6 times 6, which is 36. Same. Okay, so again, review your mathematical operations. Again, review your scales of measurement and the types of variables. For the math bit, you really want to make sure you got your basic algebra skills right and really apply those skills to your summations, at least for this chapter. We're going to take this and expand it to averages, means, and median, and mode, and later on in chapters 3 and 4, we're going to talk about standard deviation, which is derived from variance, which is derived from sum of squares. Okay, so we're going to talk about that in the coming chapters. So that's it for chapter 1. We have defined key statistical terms. We have defined key measurement terms. We have defined key research terms. Okay, the different research methods. We have described the place of statistics in science, why we need this, and we have applied and we started using summation notation when we add up all the scores together. So that's it for chapter 1, guys. Make sure you practice along with your textbook. Make sure you get as many practice questions out there as you can. Practice those learning checks if that's all you got, and use your textbook and do those questions. Make sure you practice a lot, because every class is going to be a practice quiz and or test. And sometimes in this 9-week course, you get multiple practice quizzes and sometimes a practice quiz and a test in the later weeks. So make sure you spend this time during the week, at least 10 to 20 hours a week, budgeting your time, maybe 2 hours per chapter, and include time to practice those questions as well. If you got any questions, you can email me, my Alexander College email if you're taking this course at Alexander College, or post on the Canvas course discussion board, and keep going. We'll see you in the next one.